The Yellowstone Volcano Observatory maintains a constant, vigilant watch over the entire caldera system. If an eruption were to occur, it would not be a surprise. As of 2026, the official alert level is normal, or green. Extensive geophysical data shows no evidence of magma rising toward the surface. Modern monitoring stations provide real-time data. We use continuous seismic processing and satellite-based ground deformation tracking to ensure the system remains stable. Yellowstone is often misunderstood. It is not a single mountain, but a vast caldera system. This geologic map shows the boundaries of the caldera, which formed after immense surface collapses. Unlike traditional composite volcanoes, which build upwards, a caldera forms when the ground subsides. The supervolcano label refers to its capacity for a VEI 8 eruption. This represents the highest explosive magnitude, capable of ejecting over 1,000 cubic kilometers of ash and rock. In short, Yellowstone is a massive geological plumbing system defined by its caldera structure rather than a mountain peak. Understanding the risk of a supereruption requires looking at the raw probability. Current scientific estimates place the annual chance of a major Yellowstone eruption at 1 in 730,000. To put these odds into perspective, they are remarkably similar to the mathematical probability of being struck by a meteorite. In geological terms, this represents a hazard that is extremely low on an annual basis. Ultimately, nature functions on deep time. These statistics remind us that while the geological system is powerful, it is not an immediate, recurring threat. A common misconception is that the Yellowstone caldera is overdue for an eruption. This fear is rooted in the belief that volcanic activity follows a predictable, repeating clockwork schedule. However, geology does not operate on a clock. The intervals between major eruptions are not predictive patterns. Statistically, volcanic activity is stochastic, not periodic. Eruptions are not scheduled events. Attempting to apply a countdown to the Yellowstone caldera misunderstands the fundamental nature of volcanic systems. Geophysical imaging confirms that the Yellowstone magma chamber is largely crystalline, with only 5 to 15% of the system being molten. This is a critical observation, as the threshold for a large-scale supereruption requires a melt percentage exceeding 50%. Most observed activity at Yellowstone is hydrothermal. This is driven by water interacting with geothermal heat, not magma. Magmatic activity involves magma rising from depth. These are true volcanic eruptions, which are rare and do not characterize daily park events. To recap, hydrothermal events are steam-driven explosions of water and rock. Magmatic events involve deep-seated volcanic processes that represent the true risk of eruption. Between 2018 and 2023, the world's tallest active geyser, Steamboat, showed an unprecedented spike in eruptive activity. This prompted public alarm regarding the state of the Yellowstone volcano. However, extensive monitoring confirmed that this activity was confined to shallow hydrothermal plumbing. Changes in precipitation and pressure in surface chambers drove these eruptions, not deep-seated volcanic movement. Steamboat's activity serves as a vital case study. It teaches us that surface geothermal fluctuations are frequently independent of the larger, stable magma reservoirs deep underground, keeping our assessment of Yellowstone's alert level at normal. The Yellowstone Volcano Observatory maintains an extensive state-of-the-art monitoring network. This system includes seismic sensors that detect ground vibrations and GPS stations that measure sub-millimeter ground deformation, helping us track the subtle breathing of the caldera. Advanced satellite and thermal imagery allows scientists to monitor surface temperature shifts. This data helps distinguish between standard hydrothermal activity and more significant volcanic unrest, providing a clear view of the caldera's thermal footprint. To ensure continuous oversight, even in harsh winter environments, remote stations use satellite-based connectivity to beam data to the YVO. This persistent flow of information is what allows us to keep the park at a green status with such high scientific confidence. As of 2026, advanced AI-driven seismic processing allows researchers to distinguish instantly between tectonic earthquakes and potential fluid-related volcanic tremors. By analyzing these specific waveforms, AI models detect the difference between the sharp, impulsive signals of tectonic quakes and the more sustained, irregular noise produced by fluids moving within the volcanic plumbing system. This deeper insight enables us to map the geological features of the caldera with incredible precision, separating normal background hydrothermal noise from magmatic unrest. By automating this process, we move from reactionary monitoring to proactive, high-fidelity geological insights. The Yellowstone hotspot is a migratory feature of the North American plate. As the tectonic plate shifts, the hotspot leaves a trail of volcanic centers spanning millions of years. Geological data indicates this system is not a permanent fixture. Over time, the intensity of the hotspot has been waning, showing a gradual, long-term cooling trend. 640,000 years ago, the Lava Creek Tuff eruption occurred. This event remains our primary baseline for modeling supervolcano behaviors today. This eruption ejected over 1,000 cubic kilometers of material. The resulting ash clouds created a global volcanic winter, significantly altering the Earth's climate by reflecting solar radiation. Today, researchers use this historic eruption as a benchmark. It helps define the potential magnitude and environmental footprint of a major supereruption in North America. Yellowstone's volcanic system is driven by a complex subterranean plumbing network. The structure includes a shallow rhyolitic reservoir in the upper crust, fed by a deeper, hotter basaltic reservoir below. The deep basaltic heat source provides the energy required to drive the park's famous hydrothermal features like geysers and hot springs. The Yellowstone Volcano Observatory prioritizes real-world data. Scientists monitor ground deformation using high-precision GPS sensors to ensure the stability of roads and facilities across the park. Advanced seismic monitoring is essential. By analyzing specific vibration patterns, we distinguish standard tectonic quakes from volcanic activity, allowing us to respond to localized hazards like mud pots or steam vents. This data integrates into a risk governance framework. It is not just about detecting massive eruptions, but about managing daily risks and ensuring visitor safety in geothermal areas. Hydrothermal events, not supereruptions, are the most probable hazards. By monitoring the plumbing system constantly, we keep the public informed and infrastructure safe. Human civilization operates on a remarkably short scale compared to the vastness of geological time. Our history spans a mere 10,000 years. In contrast, the Earth has been evolving for 4.5 billion years. Events that feel imminent to us are, to the planet, rare, slow-motion processes. Geologists use complex charts like these to categorize Earth's history into eons and eras. This deep time reveals that major volcanic events are separated by hundreds of thousands of years. When we monitor a system like Yellowstone, we must look beyond our own short lifespans. We are observing a naturally cooling, stable system functioning on a scale of millions of years. Because the system is so well monitored, scientists would detect the precursors, such as increased seismic swarms and rapid ground deformation, well before any catastrophic event. The internet is full of speculative narratives about Yellowstone. Many of these sensational claims lack geological evidence. For accurate data, rely exclusively on official updates from the United States Geological Survey and the Yellowstone Volcano Observatory. Science is based on physical monitoring. Real-time sensors, GPS, and seismic stations provide the data that experts use to assess the state of the volcano. Next time you encounter a claim about Yellowstone, verify it at volcanoes.usgs.gov. Rely on peer-reviewed research, not viral alarmism. Volcanic activity is a fundamental, natural part of Earth's ongoing geological cycle. Yellowstone represents only one of many active systems across our planet. Global plate tectonics drive this activity, most notably along the Ring of Fire. While systems differ, Yellowstone's activity is part of the same natural engine that shapes our continents over deep time. Experts monitor these systems closely, and Yellowstone's current state of stability is entirely consistent with observations over the last several centuries. Understanding Yellowstone within this global context reminds us that we live on a dynamic, changing, yet stable planet. In conclusion, the scientific findings are clear. First, the Yellowstone system is waning. The hotspot is gradually cooling over geological time. Second, there is no current evidence of magma accumulation or dangerous migration toward the surface. Finally, the concept that an eruption is overdue is scientifically unsupported. Geological events do not follow a precise schedule. These findings emphasize a stable, well-monitored system that poses no immediate volcanic threat. Yellowstone is one of the most closely monitored volcanic systems on Earth. A vast network of sensors, GPS stations, and satellites continuously tracks the smallest signs of change. Understanding the distinction between safe hydrothermal features and deeper magmatic threats is essential. Hydrothermal activity involves surface steam, while magmatic activity remains safely deep within the crust. Yellowstone remains a natural wonder. By relying on objective science and continuous monitoring, we can appreciate the park's majesty with peace of mind. Nature is best understood through evidence.